Hi, my name is Chefalas, and today we'll be showcasing proof by induction. In this video, we'll prove that 9 to the nth power minus 1 is divisible by 8 for all n that is greater than 0 through proof by induction. In other words, we'll prove that all powers of 9 that are greater than 0 that are subtracted by 1 are divisible by 8. Since the problem is asking us to prove this for n greater than 0, we will be using weak induction to prove our claim. Before we start a proof, we often like to build intuition about the claim we like to prove. Testing our claims will give us a better idea as to how we might go about proving this problem. To build intuition for our problem, we will test our claim for when n equals 1, 2, and 3. When n equals 1, we substitute 1 for a value of n to get 8, which is divisible by 8. When n equals 2, we substitute 2 for our value of n to get 80, which is divisible by 8. Lastly, for n equals 3, we substitute 3 for a value of n to get 728, which is also divisible by 8. After testing our claim for a few values of n, we were able to see the truth of our claim as well as some trends. Seeing that p of n plus 1 equals 9 times p of n plus 8, it seems that we can prove our claim by building an expression that we assume to be true using our weak inductive hypothesis. Using this expression, we can prove our inductive step to be true. Now we begin our proof by weak induction. At the beginning of our proof, we first state our claim as p of n says that 9 to the n minus 1 is divisible by 8 for all n greater than 0. Then, to let the audience know what method we are using, we will say that we're proving our claim with weak induction. Now we will state and prove our base case. Since our problem asks us to prove our claim to be true for n greater than 0, we will be proving our claim by weak induction with a base case of n equals 1. Through substitution, we will show the audience that p of 1 holds true. As you can see, p of 1 equals 8. And since our quotient 1 is a positive integer, our base case for p of 1 is true. After proving our base case, we say our inductive step along with our weak inductive hypothesis. For this problem, our inductive step is that for all integers k is greater than or equal to 1. If p of k is true, then p of k plus 1 is true. To prove our inductive step to be true, we will be using our weak inductive hypothesis. Our weak inductive hypothesis allows us to assume that p of k is true. Whenever proving equivalence through induction, it is often very helpful to create an expression from our inductive hypothesis that we can use later in our proof. Using our weak inductive hypothesis, we can say that 9 to the k minus 1 equals 8x, where x is a positive integer. Through the process of algebra, we can convert that equation to say that 9 to the k equals 8x plus 1. This setup using the weak inductive hypothesis will come in handy when proving our inductive step. Now when we prove p of k plus 1, our inductive step to be true. We know that p of k plus 1 states that 9 to the k plus 1 minus 1 is divisible by 8. Through rules of exponents, we can rewrite 9 to the k plus 1 as 9 times 9 to the k. Thus, p of k plus 1 can be written as 9 times 9 to the k minus 1. As concluded by our weak inductive hypothesis, 9 to the k equals 8x plus 1, where x is a positive integer. Thus, p of k plus 1 can be represented as 9 times 8x plus 1 minus 1. Through distribution and factoring, this equation can be converted to 8 times 9x plus 1. And since x is a positive integer, 8 times 9x plus 1 will always be divisible by 8. And by proving p of k plus 1 to be divisible by 8, we prove our inductive step p of k plus 1 to be true. Upon proving our base case in our inductive step, we will now enter proof with the conclusion of how we proved our claim. So we first proved our claim to be true by proving our base case for n equals 1 to be true by substitution. After proving our base case to be true, we then proved our weak inductive step to show that for all integers k is greater than or equal to 1, if p of k is true, then p of k plus 1 is true. Using our weak inductive hypothesis of p of k, we converted 9 to the k to an algebraic equation that we assumed to be true. Then we applied the algebraic expression to p of k plus 1, which we then proved to be true. Lastly, by proving our base case and inductive step, we prove our claim p of n for n greater than or equal to 1 to be true through weak induction. We then end our proof by stating QED. To sum the video as a whole, we first understood the problem by building intuition. Secondly, we began our proof by saying our claim p of n. Third, we told the reader what method of induction we were using in our proof. Fourth, we stated and proved our base case. Fifth, we stated our inductive hypothesis and built an expression we assumed to be true using our weak inductive hypothesis. Sixth, we proved our inductive step p of k plus 1 to be true using our weak inductive hypothesis. And lastly, we ended our proof with a conclusion as to how we proved our claim. So this is an example of how you prove a claim p of n to be true through weak induction. Thank you for watching. Bye.